Fantastic. And so the story I want to tell you today very much fits into this combinatorial framework for rank functions, persistence diagrams, Mobius inversion that we've been hearing so much about in the talks previous. But it's more of a metric story that I'm going to tell today. And it's a metric story in a somewhat less general setting than the multi-parameter, the poset, the various generalizations we've seen today for diagrams. So I should say that this is joint work with Leo Betthauser and Peter Bubinek. And to remind you what this one parameter setting that I'm interested in talking about looks like, the objects that we'll be looking at here are going to be persistence modules that take as input real values and they spit out vector spaces. If you're a stickler for the algebra, let's call them tame. Maybe you can think of something arising from a filtered simplicial complex like this one. And of course, the simplest, or maybe the core algebraic, well, I should say combinatorial perhaps, description that you can give of this persistence module is its rank function, which I'll take to be a function on the upper half plane. This doesn't include the diagonal. And what information is encoded here? It's something like, the value at 4, 6 is 2, and that corresponds in the filtered complex to the 2 holes that are alive and haven't died by time 6. Great, and so this, at least in the one parameter setting, gives you, in fact, all of the information that you could want to know, even in the algebraic sense, about the persistence module. And 2016, 2017, Amit's paper, rephrasing the standard description of persistent homology this way is in terms of Mobius inversion. So we usually think about the persistence diagram for these things rather than the rank function or along with the rank function. And you can get this via an inclusion-exclusion formula, but because I want to talk about metric properties today, let me just say that the property that characterizes the persistence diagram here is just that the persistence diagram is the function, again on the upper half plane, where if I want to know a value like 5, 6, then I sum up the values, or sorry, if I want to know the value of the rank function at 5, 6, then I sum up the persistence diagram values. So these blue disks indicate a value of 1. So I get 1 plus 1 equals 2. Okay, so far so good. And if, for instance, you can prove this in a few different ways, but if you know the typical barcode type decomposition theorem for one parameter modules, then you know that this Mobius inversion, the persistence diagram, takes on non-negative values everywhere on the upper half plane. This is actually, at least from the perspective of traditional persistent homology, is a somewhat innocuous requirement, but for instance, is fairly important if you want to generalize, say, like bottleneck stability. So this is something that Amit and Alex have looked at, and as well as other people in other settings. So great, I'll leave that there, but for now, to continue telling this story, you might not be surprised with Peter being on this project that we saw this paper come out and about Mobius inversion, and we were also thinking about persistence landscapes. So let me remind you briefly that persistence that persistence landscapes are something that you associate to a persistence module, and it's a sequence of piecewise linear maps. So lambda 1 here is a function which traces out the part of the rank function which has at least rank 1. Lambda 2 is the outer envelope of the region that has at least rank 2, and so on. So we get this sequence of piecewise linear functions. And of course, Peter introduced these to do statistics, to do vector algebra. Alex talked in the previous talk about what he called linearizations. So this is one such linearization of rank functions of persistence diagrams. But we were hopeful to put this into the combinatorial framework. For now, let me emphasize that these are, when you look at this definition, you get piecewise linear functions, and the functions have slopes plus and minus 1. So they're completely characterized by their critical values, where the directions change. So if you want to fit persistence landscapes into this setup, I can happily say that we were successful at this, and this is the idea. At the top, you have that same rank function and persistence diagram that we've been looking at. And what you can introduce is, instead of looking at the rank function, you can look at something that we call the graded rank function. So this is the first graded rank function corresponding to this module. And it just takes values 1 wherever the rank was at least 1. It takes values 0 wherever the rank was at least, or sorry, everywhere else, which should sound fairly familiar in the transition between slides. Similarly, you can define the second graded rank function and the third, so on. And then you can Mobius invert these. The relationship is the same relationship that we had before between standard persistence diagrams and the rank function. So if I want to know the value of the graded rank function at this point, I look up and to the left, I sum up a positive 1, I sum up another positive 1, and then these hollow circles are negative 1s. And so I do plus 1, minus 1, and that gets me the 1. Okay, and that function, incidentally, is what we call the graded persistence diagram. So this is the first graded persistence diagram for this module. A place where negative entries appear very naturally, and so there's a correspondence that you can prove between these graded diagrams and landscapes, and it's actually quite close. So the correspondence is that the kth graded persistence diagram has positive 1s exactly where the landscape has local maxima, has negative 1s exactly where the landscape has local minima, and has 0s everywhere else. So this is a complete characterization of the persistence landscape in a combinatorial and a persistence diagram framework. Now, it's interesting because this allows you to use the combinatorics to say interesting things about the persistence landscape, but today I'm trying to tell a metric story. So in fact, I want to go in the opposite direction. And what I'll say is that this correspondence puts really significant constraints on the structure of these graded persistence diagrams. Because they correspond to landscapes, they must occur in these kind of zigzag structures with +1, -1. Now, the natural thing then that anyone asks, if you're following the original story from persistence diagrams land, is, can you get bottleneck stability? Usually, but stability more generally. So let me remind you very briefly that for standard persistence diagrams, so these are persistence diagrams which do not take negative values, the Wasserstein distance between two diagrams like the circles and triangles here is just the cost of the minimum cost matching between the two diagrams, and also I allow myself to match to the diagonal. So we've seen quite a bit of discussion of this in Alex's talk, for instance. And I'm going to use the p-norm for both the inner and outer cost, in fact. So this is a range of metrics at the extreme ends. P equals 1. Everything, all of the costs are just summing things up. At p equals infinity, everything's taking a max, and then you're kind of interpolating between these two. So the immediate question, of course, is what one does when you have negatives in the mix. And this is a question that Alex and Peter, I'm glad Alex gave the talk just before mine, were thinking about at the time as well. And they gave this is the correct definition. It's really the only definition you can give. And if you want to think of it in symbols, you can say that the Wasserstein distance between two diagrams with negatives is you flip the negative parts of both diagrams to the other side. I think it's easier to think of the picture. So the Wasserstein distance now becomes the cost of a minimum cost matching, where you're allowed to do three different types of things when you match. You're allowed to match positive points to positive points. You're allowed to match negative points to negative points. And you're allowed to match positive points to negative points in the same diagram. These are the three things that you're allowed to do. And in fact, what Peter and Alex found pretty quickly when they were looking at these, at this construction, is that this doesn't satisfy the triangle inequality for anything except p equal to 1. And we had some discussion of that in the questions, in fact, after the last talk. But the examples they were looking at the time weren't structured like graded persistence diagrams. And there's so much structure from landscapes. You might be hopeful that it's enough that you could do something with it. So this is the first kind of warm up to thinking of these metric properties, is in fact this doesn't work. So you still only get the triangle inequality for p equals 1, even when you restrict yourself to the structure of graded persistence diagrams. So this is the bottleneck distance for an example. So the bottleneck distance between circles and triangles here is 2. That comes from the x-coordinate. The bottleneck distance between circles and squares here is 1/2. This comes from this y distance. And then it's 1 for these other pair, and that comes from the x distance again. And so the triangle inequality set would say that this 2 over here needs to be less than or equal to 3/2, which of course it's not. So this is a counterexample. So on the one hand, this is not enough structure to get you anything except the 1 Wasserstein distance. But if the natural question becomes, what additional things can one say when you do have the 1 Wasserstein distance? And the first of these, or the first part of the stability theorem that we were able to figure out is pretty nice. If you have the D and E here, I will call ungraded persistence diagrams sometimes. The ungraded distance, if you take that and multiply it by 2, then that gives you an upper bound for the graded distance between any specific graded diagrams. So this is what a Lipschitz stability type result, and the Lipschitz constant is 2. But also something else that's interesting is you might be interested in kind of like bi-Lipschitz type statements as well. And what you can find is that the ungraded distance is also at most the sum of the graded distances across all of the grades. So this is an interesting payoff. This actually, you can prove this part using the combinatorial setup. So this is kind of nice. And then you can also give a bound on the sum of all of the grades, and this comes from the previous statement. You get some constant times the ungraded distance on the other side. And these bounds are sharp, so we'll talk a little bit about this. I'll note that this k is the maximum number of points. So this is the maximum rank of the 2 modules that you're considering here, or the maximum number of points counted with multiplicity of the 2 ungraded diagrams. So in general, there is in fact no fixed constant that you can put here and get that the sum of the graded distances is less than equal to the constant times the ungraded for all D and E. So I can just push that k up as far as I want if I fix a c here. That's a formal statement. I think the real higher level takeaway is that we explicitly have examples where this graded distance between between modules sees more than the ungraded distance when you sum it up this way. Okay, so somehow also I want to emphasize here that one of my takeaways is that there's not enough structure to get you anything other than the one Wasserstein distance. So I kind of wanted to say this in response to some previous questions. My feeling is that it would be very challenging to find something that has enough structure to that arises naturally. That has enough structure to do this. But on the other hand, we do have enough structure to do a stability result. And for the rest of the time, I wanted to give some idea of how this result goes. Because while it resembles parts of the standard bottleneck distance proof, it's fairly different, and it uses this correspondence with the landscape really carefully. So first, again, a little bit of a warm-up. This is one for the one Wasserstein distance, and it's an example where the bound, the Lipschitz bound is tight or sharp. So this will give you an idea of why this bound is 2. And the two persistence diagrams, D and E, in this example are circles with squares and triangles with squares. So they only differ by this one point, and it's translated by 1. And they otherwise share these squares. If you like, that's the matching that will give you the one Wasserstein distance of 1 between the two of them. And then when you go and look at the graded persistence diagrams, you get a distance of 2. And where's this 2 coming from? Okay, and this is what I wanted to emphasize on this particular slide. This 2 is coming from, okay, I get the 1. Morally, the 1 is still from just moving this 1 point. I get the second, I get the 2 because I also moved a negative point whenever I move this positive point. And that's how I get 2 in both of these situations. And then at the top rank, I get 1. So this is an example for when that particular bound that we saw in the theorem is tight. All right, and now the other part of the proof to give you an idea of how you might go about proving stability for these things. And I think what's useful to say is the way I tend to think about the bottleneck stability theorem, at least in the formulation that is quite close to the original formulation. I guess this would be the isometry theorem. When you're doing the isometry theorem, you're trying to show that two persistence modules have the same interleaving distance as the bottleneck distance between their diagrams. And you do that by finding a geodesic between the modules in the interleaving distance, and then watching what happens in the bottleneck distance along this geodesic. So we're going to do the same thing. We're going to define a geodesic, but now we're doing a geodesic between two ungraded diagrams, and we're going to watch what happens to their graded diagrams as things progress. So this gives you the definition of a geodesic. And here's something fairly simple that you can observe, is that if you have any two regular persistence diagrams for the one Wasserstein distance in particular, there is a geodesic between them that moves 1 point at a time, 1 coordinate at a time. So let me show you what this geodesic looks like. The squares are going to be the geodesic, and we're going to watch it like a movie. So the first part of this is we're going to move this circle point to the triangle, first along the x coordinate, and then along the y. And then we can do that 1 point at a time for every point. Okay. So that's the first step in breaking down into a nice, this tells you what our nice geodesics are going to look like initially. Sorry. So we'll call these coordinate geodesics. Now once we have these coordinate geodesics in hand, we we need to characterize what happens to graded persistence diagrams as you move along a coordinate geodesic. So I'm going to look at this persistence diagram, and also the graded persistence diagram for this one that I'm going to look at is the second, and it's going to look like this. I've drawn in the black lines. The black lines are technically not part of the graded persistence diagram. They're just representing something about the landscape, but I find it easiest to visually track what's going on when you draw these in. And what's going to happen is we're going to watch as this circle up here moves to the right along a single coordinate geodesic. And before you cross this line along with this other circle, the graded persistence diagram doesn't change. But when you do go over the line, the first event that happens is that this square starts to move. The second event that happens is you cross this next line, and now this square starts to move, and this negative point starts to move. So this thing locks in place. Eventually, you drag it far enough right, and that negative point goes into the diagonal, and you change structure again. And then finally, if you were just continuing all the way to the right, the circle goes into the diagonal itself, and you're left with this structure. So visually, this really gives you, hopefully, the core of the idea of how you would prove stability. You finally can break a geodesic between two diagrams, D and E, down into these extremely simple pieces. You have one coordinate moving one point at a time. And if you do it carefully, you can use the structure that's induced on these graded persistence diagrams by being persistence landscapes, or being corresponding to persistence landscapes, to give 5 different ways the structure can change at different events. And for each of these 5 different types of events, you can give matchings, you can give geodesics now for the graded persistence diagram that don't exceed twice the distance between the ungraded version that you were looking at. So that's it. That's the core of the proof. And really that's the end of my talk. Again, I hope that the key takeaway here to me is trying to give some idea of, so these arose very naturally as persistence landscapes, which are fairly widely used and well studied. They have negative values in them, and it hopefully gives you an idea of at least the quantity of structure we needed to prove a stability result. And I hope that illustrates, as we all kind of continue to think about these things, what other results or generalizations might have to look like. But otherwise, thank you guys. Thank you for your time and attention.
Thank you, Parker. All right. Any questions for Parker? Parker, could I ask a question first?
Of course.
On page 9, you introduced that the metric that was introduced by Alex Melchison and Peter Rubenick, and you mentioned here that this metric is the correct one, right? Like, could you more elaborate on what you mean by that? This is the correct one.
I think the magic words to say here are that this is the metric that respects how you would think about this as like growth and deke group closure type thing. So yeah, I think that's the right thing to say.
Okay. Nice.
So I mean, it's a good question because, you know, what maybe it's not the right thing because it doesn't work except for p equal to 1. But at least that, I think, is the motive for this particular generalization.
Yeah, I was just curious. Yeah, any other question for Parker? Oh, there was a... Oh, Tamar, go ahead.
Sorry.
Hey, Parker, I was just wondering, did you think about how to compute it? Or does it follow from the usual W1 Wasserstein distance computation? But I guess there is some difference here.
This is a good question. It's very computable for exactly the reason you say. So the good news is that because of this correspondence with landscapes, you could take this is actually happens to be almost by accident in some ways how Pavel Delotko's package for computing landscapes computes these things. So it stores the critical values of the landscapes. So you can kind of immediately, with this code, from a practical standpoint, get the critical points. And then, exactly as you say, if you you know which is positive and negative, and so you can go do a Wasserstein calculation and just flip it over. So it shouldn't be too expensive. I haven't yet done it, and this is a good question. I have this on the list to go throw it at something and see what happens. But
Thanks.